much, Stephen, for the introduction, and thank you to the organizers for this very beautiful conference workshop. It's a pleasure to be here, surrounded by beautiful Alps. Okay, so today I will talk about cluster promotion maps, Amplitudes, and Amplituhedra. And for me, like the major threads of intersection between physics and algebraic geometry and combinatorics has been via mainly two directions, which is one is related to positive geometries, that here I sketched the pictorial representation of the Amplituhedron, or artistic representation. And on the right-hand side, we have cluster algebras. So this is, of course, an Amplituhedron. It appears in many contexts, but here I took it as a cartoon, as a combinatorics encoding a certain types of cluster algebras. So we have these two threads, which one is like the Amplituhedron, that in physics, as we know, geometrizes scattering amplitudes without, let's say, in a way that the amplitudes are computed as volumes. On the other hand, cluster algebras, we've heard a lot in this conference. It's a class of commutative rings with a set of distinguished generators, and they have a remarkable combinatorics, and many algebraic varieties that we love have a cluster structure. So like Grassmannians, Schubert varieties, Flag varieties, and many others. And there is like beautiful connections, and motivated also by connection to total positivity and Lie theory. Then the Amplituhedron, of course, was first originated in physics, defined by Yaron Nima. It also led to very beautiful developments in mathematics, and it's nice to see that after more than 10 years since its definition, there are more and more mathematicians working on it and discover new connections, because of course it has connection with the theory of total positivity and also the matrix, and also more importantly was one of the first and major, let's say, conjectural example of a positive geometry. On the other hand, cluster algebras are very, very useful in physics as well, as we have heard, in connection to the cluster bootstrap and understanding singularity of scattering amplitudes. However, not many connections were known between the Amplituhedron and cluster algebras, at least on the math perspective. There was no a priori reason to expect these two things were connected, but of course also coming from physics that we expected that these things should have some connections. So today I will talk about a new way to generate what we call the cluster maps, say, from the Amplituhedron, and I will, in the first part, I will go through, let's say, part of the review, or to understand how this, the combinatorics of Amplituhedron is related to amplitudes. I will also mention relation to BCFW tilings, and we have three of our works with some of the people here, and then some upcoming works. So the first work was in the first two were published. The third one is under review. We submitted, and the last work is in preparation. And these works are with joint works with different subsets of the authors, and I, Lauren, and Zvika, of course, are here. Okay, so I start with an introduction. I will start with the background to explain mostly what the positive Grassmannian, Amplituhedron, and cluster algebras are. We've already seen this concept somehow in some form, so I will not be too detailed, but of course you can stop any time to ask questions. There are experts in the room about any of these topics, but not everyone is expert on all of them. Then I will mention how amplitudes, the Amplituhedron and cluster algebra, so basically the mathematical objects that I define in the backgrounds, are connected with each other, and in particular how related to amplitudes. And then in the last part I will mention the connection with cluster promotions, define cluster promotions, and understanding how these are related to the Amplituhedron and amplitude, and give some outlook. Okay, so let me start with setting up the notation. We already seen the Grassmannian GRKN is a space of k-planes in n dimensions, and we can represent an element of a Grassmannian by full rank k times n matrix C up to row operations. And we also want to use something called Plucker coordinates that we denote as angle brackets I, which we'll denote as the maximal minors of the matrix C computed with the column set I. So for example, the matrix C is 2 times 4 matrix, and if you compute the Pluckers 1, 2, it's the determinant of the first two columns, submatrix obtained by picking the first and the second column, and it's 0, and the Plucker 1, 3 is obtained by computing the determinant of a submatrix obtained by picking the first and the third column, and so on. So we list all these numbers, n choose k, and we consider them as coordinates of our point in the Grassmannian. we are interested in also in a particularly nice subset of the Grassmannian called informally deposited Grassmannian, originally the totally non-negative Grassmannian, denoted by GRKN greater or equal than 0. And it's a subset of the Grassmannian where all the Plücker coordinates are non-negative. Okay? So here, with the Grassmannian, sometimes I think it as a complex Grassmannian. Here I took it real, but we will also think about complex. But of course, when we talk about positive Grassmannian, it's going to always be real. It's a semi-algebraic set. You can think it inside the complex Grassmannian or inside the real Grassmannian. Okay, so importantly, we can partition the positive Grassmannian into pieces according to which Plücker coordinate is 0 and which Plücker coordinate is strictly positive. So if I denote, we can label cell as with the sets M. M is a collection of labels of the Plückers that are strictly positive. So a Plücker is positive, then the label I is going to be part of our collection. So for example, here you can see that all Plücker coordinates of this matrix are non-zero except 1, 2. So M would be like collections of all 2-element subsets of 1 through 4 except 1, 2. And since everything is non-negative here, all the Plückers are non-negative, C represents a point in the positive Grassmannian 2, 4. In particular, it also belongs to the piece S sub M because 1, 2 is 0, so it's as the Plücker is 0. Okay, so we can always do this. I mean, no one is preventing us from doing that, but the nice result is that Poznikov showed that whenever these pieces are non-empty, they are homomorphic to open balls, and there is a nice decomposition of the positive Grassmannian into cells that are called positrate cells. There are extra nice properties about it. There is a regular CW complex, and the closures is there are extra nice properties of these, topological properties of these cells, but for our purposes, we want to say that there is a nice combinatorial description of these cells, meaning that there is a bijection between the cells and some nice combinatorial objects. And for today, I will consider mostly Plebit graphs that I will define in the next slide. So this means that if I have a combinatorial object, I can understand everything from the cell, like its dimension, which Plücker is 0, parameterize a point, everything, just from the combinatorial object. Okay. So I will define Plebit graphs. Also, throughout this talk, sometimes I will slightly simplify definitions or statements to make it not too technical. So if you're expert in the room, you can ask me later or even during the talk if there is a detail that is not present. But I on purpose didn't include it because it may be too technical. Okay, so the definition of Plebit graphs: a Plebit graph G is a planar graph embedded in a disk such that each vertex is either black or white. That's why it's bicolored. And then it has vertices on the boundary of the disk labels from 1 to n, incident to a single edge. So here, for example, is an example with 8 edges, boundary edges, and then black and white vertices. So there is the theorem that says there is a bijection between positrate cells in the positive Grassmannian and equivalence classes of Plebit graphs that are related by certain moves. So if I consider graphs that are related by the moves M1, M2, and 3, I'm going to explain in a second, then I want to consider the equivalence class of these Plebit graphs, and each equivalence class can be associated to a positrate cells and vice versa. I mean, these moves are not essential for today, but most of you maybe have already seen, and there is like a contraction of, if you have a vertex of a certain color, you can expand or contract. If you have a square of this type, you can swap the colors of black and white, and if you have a vertex of degree 2, you can remove it. Okay, maybe we will use this sometimes. You can always, and this can be either black or white, and this can be either all black or all white. And in particular, So in particular, since this is a combinatorial object we have, we can label a cell S by this Plebit graph G. So SG would be the positrate cell associated to the equivalence class of the graph G. I'm not telling you exactly how to go from the Plebit graph to the details of the cell, but believe me that there is a bijection, and for now we're just using it as a label for the positrate cells. And in particular, we can say that a graph G is of type Kn if it labels a cell that is in the Grassmannian K, n. Okay. Also, we can often choose a representative of our Plebit graph, our class, such that the graph is bipartite. So we assume, for example, that the vertices at the boundaries are black, and we can always add some extra vertices using, for example, the move M2 or expanding M1 to add extra black vertices such that it's bipartite, meaning each edge is connected by black and is connected to a black and a white vertex. So sometimes we use this. Okay. Okay, so we already seen some Plebiscite graphs in the other talks as well. Okay, let me now start, if there are no questions, let me go to the Amplituhedron. So the Amplituhedron, for that we fix three positive integers, k, n, and m, such that k plus m is less or equal than n. And we also fix a matrix, Z, that is a long skinny matrix, so n times k plus n, such that it has all the maximal minors are positive, so all the minors k of size k plus m times k plus m are positive, strictly positive. So this is the matrix that we fix, and then we use this matrix to induce a map from the positive Grassmannian that we defined before to a smaller Grassmannian. So smaller because k plus m is less than or equal than n. So this map Z tilde is a map from the positive Grassmannian k comma n to the smaller Grassmannian k comma k plus m, where the map is just induced by matrix multiplication, right multiplication. So if I have an element in the positive Grassmannian represented by a matrix C, then multiplying it by a matrix Z from the right creates another matrix that represents an element of a Grassmannian in the image. Okay, this is a simple map, but we define the Amplituhedron as the image of the whole positive Grassmannian inside the smaller Grassmannian k comma k plus m. Okay, one can show this map is well defined. Also, I will drop the dependence from the matrix Z in the definition, but you can secretly, of course, think the object itself is defined by fixing Z. However, most of the combinatorial properties I'm mentioning will not depend on Z. Okay, so before moving on, there is like a family with 3 infinite parameters. We can try to see which ones are known, which ones are we cover something known. So when k equals 1 and m equals 2, we get back convex polygons with n vertices in RP2. For example, this is when n equals 6, k equals 1, and m equals 2. And we can think about the rows of the matrix Z as the vectors giving the vertices of our polygon. And the fact that C is positive means that we are taking the convex hull of these vectors, so we are inside the polygon. Okay, with the Amplituhedron we get, let's say, a pointed cone. We get in the projective space because we basically think about it as slicing a pointed cone to get this polygon. For generic M, we get a polytope with dimension M with the n vertices, and it's a particular type of polytope called cyclic. Here it's a 3-dimensional one. It's an E-ring. Okay. Finally, if k is, so k equals 1 is the minimum value, and k equals n minus m is the maximal value of k. When in this case, this Z matrix is a square matrix, and so this map is just giving you an isomorphism, sorry. That means that the image itself can be identified with the domain, which is a positive Grassmannian. But what happens in between, it's like a new family of objects that have been studied. M equals 1 gives you some bounded regions or chambers in a cyclic hyperplane arrangements by Stephen and Lauren. This is a nice picture from their paper. Then for m equals 2, the Amplituhedron itself is nonlinear, so it's not a polytope or sliced by some hyperplanes. It's a real nonlinear object, but with work by Tomek and Lauren and Melissa and some subsets, different subsets of them, we show that there is a very tight relation to a very beautiful polytope. This is a hypersimplex, and also a very beautiful object in tropical geometry, which is the tropical positive Grassmannian. But today we will focus on m equals 4, which is of course very important, and its volume somehow was conjectured to give a 3-level scattering amplitude in n equals 4 Cyprian-Mills, where n is the number of particles and k is a so-called helicity sector for nk MHV amplitudes. And in particular, to compute this volume, we tile the Amplituhedron and then sum over the volumes of each tile. So that's the way we compute. So the calculations of amplitudes in this way can be translated to the combinatorial problem of finding a tiling. And then we sum the volumes of the tiles and we get the volume and the amplitude. So this was somehow the roadmap.
Sorry, Matteo, what's that picture?
Sorry?
What's that?
So this is like a picture from the particle collider at CERN of particles happening. Yes. Yes, I should have put citation here, but it's just to say that this gives some scattering amplitudes. It's not a geometric object. It's not a geometric object. It's the real traces of particles scattering. Okay, it doesn't look like the Amplituhedron. Okay, so now let's talk about tilings and tiles. Of course, let me define them and motivate a bit further. So the positive Grassmannian has a nice cell decomposition, and the Amplituhedron is the image of it. So it's a natural question whether we can use the images of these cells to tile the Amplituhedron. So in particular, I want to define a tile in this way. So if I start with the positive cell S, I want to consider its image in the Amplituhedron, and we call it a tile if the image is full dimensional and the map Z tilde is injective on the cell. So remember that the positive Grassmannian is much bigger than the Grassmannian in the image, so in general it's not injective, the map. But if we restrict to like smaller dimensional cell of a proper dimension, in the positive Grassmannian there's a chance this map Z tilde is going to be injective, and we want to understand exactly which cell has this property that it's, the map, Amplituhedron map is injective. And then once we have a tile, we want to use it to cover the Amplituhedron. So a tiling is a collection of non-overlapping tiles that cover the Amplituhedron. Okay, so it's a very natural definition. So when the Amplituhedron is a polygon, tiles are triangles with vertices on the vertices of the polytope, and tilings are just triangulations of n-gons. So this is great. Okay, I'm not going to in details on this because, first the open problem is finding and classifying all tiles and tilings for the Amplituhedron where m is greater than 2 is a big open problem. And in particular, even if it's a big open problem, tiles and tilings I've shown already that they have a very beautiful combinatorics. So they have relation to tropical geometry as mentioned. There's a relation with magic number, something called magic number. There's also something like higher M generalization of BCFW recursions, and there are connections with cluster algebras. So for more on tilings, tiles and tilings for m greater than 4, come to Chaim's talk at the end of today. So I will not talk about tilings for m greater than 4 today. Okay, so this is the motivation for tiles, but before moving on, are there any questions regarding the Amplituhedron or positive Grassmannian? Okay. I will use one slide to summarize cluster algebras, and I'm sorry if I'm not making justice to the field, but we don't have so much time and we've already heard a lot about them. So cluster algebra is a class of commutative rings with remarkable combinatorial structures. So there are distinguished generators called cluster variables that are grouped in overlapping sets of the same size called clusters. And we can go from one cluster to another. There are relations between these variables that are encoded by mutations and cleavers. We can compare all the talks on yesterday morning. So in practice, what we do is we start with an initial cluster, and then we generate all the others by mutations. Okay? So maybe I can skip, but the mutation, if I have a cluster variable little x in a cluster, bold x, then the new cluster is obtained by mutating one variable, and so removing it and adding a new one, x prime, and x and x prime are related by a relation of this type, where mi are monomials in the cluster variables of the old cluster. Another terminology is that sometimes we want to keep some of the variables present, meaning we never mutate them. So whenever we start with a cluster, we design we kind of declare some of them to be frozen. So when we mutate to another cluster, we don't touch them. There always be present in all clusters. So they're kind of spectators in a story. Finally, another terminology that we also heard before is that a collection of cluster variables is compatible if they can be found in a common cluster. So having two cluster variables to appear in a common cluster is a non-trivial property, and this is a relevant, it's a nice question from the cluster algebra perspective, but it's very relevant for physics as we saw before. Okay, so importantly for us, we will consider the coordinate ring of the Grassmannian is a cluster algebra, is a cluster structure, and to be sure, we denote it as A, G, R, M, N. And it's the ones, found by Scott. Okay. There's a bit of reflection, I can't see much. For the Grassmannian 2, n, the cluster algebra is a simple combinatorics in terms of triangulation of arcs and an n-gon, which was what featured in my introductory slide. So in particular, it has a finite number of clusters. The cluster variables are just Fluker coordinates, and we know how to find compatibility between them by just thinking them as non-crossing diagonals on an n-gon. But for greater than 2, the cluster structure of GRM command is much more complicated. In particular, in general, there are infinite amount of clusters, and the cluster variables are polynomials of Fluker coordinates. They are not anymore just Flukers, but polynomials. There are Flukers and also polynomials that could be of arbitrarily high degree. And then, for example, this quadratic here is a clustering variable of the Grassmannian 4,7, where this is a Plucker coordinates in the Grassmannian, related Grassmannian. And in general, there is no nice combinatorial rule to decide whether two cluster variables are compatible. Only if you are Pluckers, there is something called weak separation, but otherwise, it's not a problem. Okay, there are no questions. I will move to the next slide, which basically brings all these mathematical concepts into how they interplay with the amplitudes. Okay, so I will focus on planar n equals 4 superior meals, and amplitudes in planar. So some parts of this maybe they will talk more to physicists, but hopefully it's going to be understandable by mathematicians as well. So the amplitudes in planar n equals 4 admits an integral representation whose integrand, denoted as ILKN, is a rational function of external kinematics and loop momentum, where capital L is a loop momentum and K and N has the same meaning as before. So in particular, we can think about the residues of integrand, these rational functions, on a 4L dimensional variety where a maximal set of internal propagators go on shell. So this is called also a maximal cut. And these quantities are called leading singularities. So we can think about leading singularities of the theory. We also heard about them in some of the talks this week. And these, of course, they were introduced, already at the beginning of, in the 60s, when people tried to fix the S matrix by analyticity without success. But of course, they're very relevant for n equals 4 and other theories. So the key point here is that the leading singularities can be expressed as sums of building blocks called Yangian invariants for this theory, n equals 4 superior meals. And the key connection with positive Grassmannian is that each Yangian invariant can be labeled by a positoroid cell. So I will use the Plebig graph associated to the positoroid cell as a label, YG, corresponds to a certain 4K dimensional positoroid cell inside the Grassmannian K, N. So I can label each Yangian invariant according to the Plebig graph that is associated to a positoroid cell inside the positive Grassmannian. And all these cells will have 4K dimensions. And the reason is that this is the dimension of the Amplituhedron when m equals 4, which is the one for physics. Okay. In particular, if you want to be more precise, the Yangian invariant itself can be thought as a canonical form of the image of the positoroid cells using the Amplituhedron map. So this is, if you know the framework of positive geometry, this is a very direct connection. So it's not only a combinatorial gadget to label Yangian invariants, but it's also, you can compute them literally by computing the volume or the canonical form of the image of the positoroid cells in the Amplituhedron. Okay, so now I want to define something called the intersection number because this is useful also to understand Yangian invariants. So now I want to consider the Amplituhedron map, a map as from before, but now as a rational map between the complex Grassmannian. And I want to see, I basically take the Amplituhedron map and I want to check what is the degree of the Amplituhedron map when I restrict myself to my positoroid cell as G. So if this map has degree D, then we say that the positoroid cell or the Plebig graph has intersection number D. So I will denote as the intersection number of the Plebig graph will be D if the corresponding Amplituhedron map restricted to the positoroid cell has a degree D, meaning that the pre-image will have there would have the 3 pre-images. Each point will have D pre-images in that. Okay, so I will maybe start here. I will be more precise at the end of this slide. For example, so in particular, if we fix m equals 4, we connect to physics again, because that's the Amplituhedron for m equals 4 is relevant to scattering amplitudes. And when we have, if we have a Yangian invariant associated to a positoroid cell labeled by G, and this G has intersection number 1, then this Yangian invariant is a rational function of the external momentum. In particular, the poles of these Yangian invariants corresponds to the facets of the image of the positoroid cells in the Amplituhedron. So there is a clear map between the pole structure of the Yangian invariants that are functions relevant for scattering amplitudes and the facets of these images of positoroid cells in the Amplituhedron. And this also is related to tiles, but here for now I will not mention that. When the intersection number of the Plebig graph or the corresponding positoroid cells is greater than 1, then this Yangian invariant is computed as a sum of D functions. So the number of functions which have algebraic singularities. So they will have square roots or other things. And we already seen in physics that these are very important. For example, if you are familiar with the 4-mass box, these are exactly the singularities that you get from the 4-mass box Yangian invariant. Okay. Just to be more precise for maybe mathematicians, so here I'm considering D to be the degree of Z tilde as a rational map on the positoroid variety, let's say, which is a complexification of our positoroid cell, so in a complex order. And also for generic Z, meaning that I want to be in an open Zariski subset of my space C. Yes?
You have a cap on the degree that you expect to see in the Amplituhedron for, say, MHV amplitudes, like that.
For
like maximum degree.
I mean, for k equals 1, everything is intersection number 1. For k equals 2, up to intersection number 2. And I don't remember what's the bound, but for sure, I mean, in the original paper, Jake and collaborators have a big table. I'm not sure if I conjecture any bound on them. But, yeah, for sure. Okay, I can give you some data. The first intersection number 2 cell is for k equals 2. The first intersection number 3 cell is for k equals 3. Yeah. I think Jake, in the picture of the positive Grassmannian, the book of the positive Grassmannian, there is a positoroid cell which is intersection number 2 to the 10. I don't know how he computed it. Yeah. So
to be clear, that correlates with the degree of the equation that the roots are solutions of, right?
Yes, exactly. This is related also to the real Schubert problems, I guess. I mean, it's like understanding how many solutions a real Schubert problem has, actually. So there is a tight connection with that. Okay. Okay, so now let's go back to the amplitudes, now that we are defining Yangian invariant. So at 3-level amplitudes for n equals 4 superior meals.
Sorry, Matteo, just hold that. Can I ask, like, do you know if you restrict, so this is like the complex degree, but would you just restrict Z tilde to the cell SG? Mm-hmm. Do you know how many, do you get?
Yeah, that's a good question. I think this question relates to the fact that, I mean, all intersection number 1 cells for m equals 4, I think they're also injective on the positoroid cells, so are also tiles. But the converse is not true in general. Like, there are some intersection number 1 cells for maybe m equals 3 or other m that are not tiles.
How is that possible?
Because
there's like specific points which are bad. Yeah.
Exactly. Yes, and in general, for higher intersection number 1 is open problem. Like, we don't know whether there is a cell of intersection number D with D greater than 1, but then the pre-images are always outside of the positive Grassmannian, and so we could still. Yeah, exactly. We don't know that. We haven't found any. For now, everything is sitting. That's how it is.
Okay.
Yeah.
So when you're talking about tiles, well, you're not talking, but do you require D to be 1 or?
Yes. I mean, no. Actually, we don't require D to be 1. No, we don't require D to be 1. We just require. I mean, the definition is just the dimension has to be correct of the cell, and then. Yeah, but in practice so far, everything had intersection number 1.
Okay.
Because we haven't found any high intersection number whose pre-images are always outside, and so, yeah. I don't know, that's an interesting question whether it's possible. But this is very related to whether the Schubert problem has, real solution or not.
That's right, yeah, that's right. Yeah,
so
that's why.
Maybe you can solve it. Okay, okay, let's go back to the Amplituhedron, to the amplitudes. Basically, for 3-level amplitudes, the 3-level amplitudes n equals 4 superior meals can be written as a sum of certain Yangian invariants. And we have certain collections of Yangian invariants that gives our 3-level amplitude. So these Yangian invariants are actually rational, so the ones that associate to intersection number 1 cells. What about loops? So of course there's been lots of talks on yesterday, but let's say schematically that you can think about loop amplitudes as a combination between Yangian invariants and some multiple polylogarithms with a star here that I will mention at the end. And so we can understand the singularity of the multiple polylogarithms in terms of the symbol, which is a sequence of certain letters. And the Yangian invariants that appear here, are the ones that I told you before. There are some Yangian invariants. So there is a kind of representation of the amplitude that looks like this. And then the connection with cluster algebras are the following schematically, is that it was conjectured that all these letters that appear here, that encodes the singularity and the branch structures of these multiple polylogarithms, that are these transcendental functions appearing in loop amplitudes, are cluster variables for 4, n. So I meant all the rational letters are the cluster variables for 4, n. And then there is also some extra structure. So when adjacent letters are compatible cluster variables, So if you find in the sequence here, if you find 2 consecutive ones, then they are compatible in the Grassmannian. There are also more. Omer mentioned, for example, if you have a triple, then the one that sits in the middle is the like exchange ratio from going from one to another. That's a kind of X variable, but it's not relevant for today. And finally, also the set of poles of every rational Yangian invariance are also cluster variables that are compatible in the Grassmannian for comma n. So every Yangian invariant here has poles, a rational function with poles that are compatible, and also, all the rational Yangian invariants appear here are also this property. Sorry. So we have lots of authors in this room have contributed to this. Lots of people in this room have contributed to these results.
Just keep being at all yourself.
Sorry?
Second time, I'm always at all.
No, I know. I thought about this, and I also hoped you would comment. But you're also no. It's because if I added your name, I would go in the other line. But you're here as well. So it's unless you're ready to sacrifice one of your students to put your.
Yeah, but they're no longer in the field. They left the field.
Well, are you suggesting I put some like ghost names here because they left?
Plus former students.
Okay.
I'll add.
Okay. Well, we all know exactly. Okay. Okay. Also, another observation is that somehow all the algebraic letters. So, all these letters can be either rational or algebraic, but somehow all the algebraic letters that appear here as singularities of the multi-poly logarithms were observed also to be singularity of some non-rational Yangian invariants. So even if, in principle, you wouldn't expect, or maybe you not necessarily expect relation between this part and this part, the singularity that are here, they're also somehow related to the singularity of Yangian invariant. So Yangian invariants themselves are very important to understand singularity of amplitudes. Beyond the fact that they appear like this, they can also be helpful to understand singularities that appear in the functions, transcendental functions, and multiplies them. So this is just an observation. Okay, it's not my observation. It's kind of feeling of community. Okay, so the start here is that, of course, multiple poly logarithms are not enough in general for describing scattering amplitudes. So there are, starting from 2 loops, 10 points, and n cube MHV. There are elliptic multipoly logarithms and elliptic leading singularities and Calabi-Yaos. But these are things. We are not at the stage where we understand very well their singularity structures. There is symbol alphabet and any relation to cluster algebras, but it's an interesting direction, so it would be important to go to. Okay, so now let me go back to let me back to three-level scattering amplitudes. So I mentioned that there are can be computed by summing a certain collection of rational Yangian invariants. Then the question is which collections of Yangian invariants, for example, gives scattering amplitudes, and this is related to tiling of the Amplituhedron. So first of all, the Brito-Cacciato effect Winton, the BCFW recursions were shown to express that these three-level amplitudes can be computed as sums of certain Yangian invariants that I call a BCFW expression. So whatever collections of Yangian invariants, whatever sums of Yangian invariants coming from the BCFW recursors, I will call it a BCFW expression. And the cells, positary cells corresponding to the Yangian invariants appearing in the BCFW expressions are called BCFW cells. Okay. So one of the theorems that we proved with our collaborators a while ago is that if we have a collection of Yangian invariants in the BCFW expressions, so that means that it gives the amplitude, then the corresponding collection of positary cells, and we let these to be the corresponding collection of positary cells, then the collection of the images of such positary cells in the Amplituhedron give a tiling of the Amplituhedron for m equals 4. In particular, different ways of performing BCFW recursions, i.e. different BCFW expressions, corresponds to different tilings in the m equals 4 Amplituhedron. Okay? So this was basically one of the major conjectures in the Amplituhedron when it was introduced by Yara and Nima, because it gives a geometric meaning to BCFW recursions as some tiling in the Amplituhedron, but also it kind of pins down the geometric origin of n equals 4 scattering amplitudes at tree level. Okay, so the special case of the standard BCFW tiling was proven in a beautiful paper by Heinz, Vika, and Ran 2 years before. And also, there's going to be more analogous extension of results for other Amplituhedra for example, the momentum amplituhedron, IBGM amplituhedron, and loop amplituhedron in the next talks. I think all today. So lots of amplituhedron today. Okay. Here just a pictorial way to define, to add the recursion. I don't want to go into details, but basically these are Lebesgue graphs associated to the cells that appears in the recursion. And the main key point is that you can obtain a tiling for the amplituhedron in m equals 4 using a tiling where you have one less particle, one fewer particle. So n is you need an amplituhedron of n minus 1. But the most important part is that you want to obtain tilings by gluing cells of smaller amplituhedron, and this will give you the very important contribution, which is related to the BCFW, how you build BCFW cells, basically. And the main thing today is that I want to say that the key of our proof, or some very important elements to solve this problem, was that we used cluster algebras to describing these images of positron cells inside the amplituhedron. So if you want to know how these images are gluing together to tile the amplituhedron, it's important to understand how to describe them. Okay, I'm realizing that I'm a bit behind time, but I started, I think, 7 minutes late, but it's okay. Okay, so in particular, let's have a closer look of the BCFW cells. So BCFW cells can be obtained recursively. In particular, if you have a BCFW cell from left and a BCFW cell right, associated to a Lebesgue graph that you can think inside this blob, and a Lebesgue graph that you can think to be inside this blob here, then we can define a BCFW cell gluing them in represented by the Lebesgue graph that is depicted here, which is obtained by gluing the left and the right blob by sticking some extra Lebesgue graph at the center and attaching the blobs to the core Lebesgue graph. So the purple, the Lebesgue graph in the center is called, we call it the core. And for the BCFW, the core looks like this, and we also call it a butterfly because it resembles a butterfly. Okay, so what I wanted to mention is that in more details to go through towards cluster algebras is that in our paper, also where we proved the BCFW tilings, we showed, of course, that each positron cell, each BCFW cell, gives a tile, meaning that their images is a tile, so it's injective and it's full dimensional. But importantly, we show that each BCFW tile, so the images of these BCFW cells, are regions in the Grassmannian where a collection of compatible cluster variables have a definite sign. So for each BCFW tile, we associate a collection of cluster variables that are compatible. Cluster variables that I denote, collections that I denote X sub G. These are collections of compatible cluster variables in the Grassmannian 4, n. And imposing that they have certain sign, then that defines a semi-algebraic set, a region in the Grassmannian, and that is exactly your image of your BCFW cell in the amplituhedron. So once we have a semi-algebraic description of the tile, it's easier to understand when they overlap and whether they tile the whole amplituhedron. Because before, we only knew, we only could see the tile as the image of some positron cell, but that's not very useful to have a notion of when they intersect in the image. Okay, so this is the major thing. And let's say as a corollary, we also have that, for example, the facets of the tile are described by cluster variable that is a subset of this collection. But by what I said before, the facets of these tiles are also poles of the corresponding Yangian invariant. So in some sense, as a corollary, we show the cluster adjacency for Yangian invariance that comes from BCFW recursions, which says that the poles of the Yangian invariant in the BCFW expression are compatible cluster variables for GR4, n. Because each Yangian invariant is the canonical form of these Z tildes S, and the poles of Yangian invariants correspond to its facets, but these facets are carved out by, are described by a subset of the collection of cluster variables that we use to describe the cell. Yes?
So, I mean, where is the adjacency in the cluster adjacency? It sounds like this should just be saying whenever they're appearing together, like be it adjacent or not, they should be compatible.
The word adjacency was a synonym of compatibility. I mean, Omer and collaborators said define cluster adjacency because originally that was a property where adjacent letters in a symbol are compatible cluster variables, and that property was called adjacency. But now, I mean, the cluster adjacency phenomena is wherever you find collections of compatible cluster variables in some physical quantities. So that's it's just a terminology to refer to this phenomenon. So the cluster adjacency for BCW invariant is by definition these statements, and that we proved. That's
An abelianized version of adjacency where everybody's next to each other.
Exactly. Okay. So I have to mention that in this case also pairwise adjacency implies pairwise compatibility implies the compatibility of all clusters. So if every pair of cluster variable is compatible, then the whole set is compatible. The whole set is a set of compatible cluster variables. Okay, but then the main question is how do we find a collection? How do we find a collection of compatible cluster variables for each BCW cell? Okay, and here already we see that each BCW cell can be built recursively, and the question is, can we build these collections of compatible cluster variables in a recursive way? Okay. Okay. In order for that, we would like to define something called a cluster map. Yes.
So you said you found a semi-algebraic description of these tiles? Oh, sorry. You found a semi-algebraic descriptions of these tiles, right?
Yes.
So can you make any statements about facets of the tiles or even faces using this semi-algebraic description?
Yes, facets. Face is a bit trickier. But facets, yes. I mean, that's what we mentioned here, that we can describe facets. Each facet lies on the vanishing of a certain hypersurface. It lies in the vanishing of a certain polynomial of Pluckers, and that polynomials are cluster variables. It's a subset of the cluster variables we use to describe our tile. So maybe I can just do as an aside. For polytopes, you just need the facets inequalities to define your polytope. You just need to say whether a point is at the right or the left of each facet, and that specifies exactly the regions inside your polytope. So as for every hyperplane arrangement. But in the Grassmannian, that's not true. So if you just, for example, the positive Grassmannian has n facets, the Pluckers where they have consecutive intervals. You have intervals as Plucker coordinates. But that's not enough. So imposing that n Plucker coordinates of the intervals are positive, it's not enough to guarantee that all the others are positive. So you need extra inequalities other than the facets. That's why it's a containment. It's very non-trivial that in some sense, our description goes also much beyond somehow the original one, because this one was also only about facets, but we also say that actually the whole thing that you need to describe the tile is associated to cluster variables that are compatible. And the facets is just a subset of this collection. And you can think them, there is a way in which you can actually associate the cluster algebra to the tile, and we think about the facets as the frozen ones. You can have many ways of describing your tile, and each way is a cluster of this cluster algebra, but in every possible way of describing your tile, you would always want your facets as variables to describe it. So they can be thought as frozen. As the positive Grassmannian, no? The frozens in the positive Grassmannian are exactly the n facets of the positive Grassmannian, and then each cluster is a different way of describing the positive Grassmannian. So similarly, the whole story, I didn't mention here, this is more in our previous paper, but that's the idea that we can associate some kind of cluster algebra for each tile, where each cluster gives a semi-algebraic description of the tile. With the difference that we have to assign some signs to the cluster variables. It's not just positive as for the positive Grassmannian.
I guess the purple thing is the butterfly that you mentioned. And just an example of it, random example, is a very specific form of it where you have an asymmetric graph there. Like, is it important that there's a white blob there? It's also just one example.
Yeah, okay. For every BCW is obtained like this. But with the addition, so you want to do some cyclic sheaves, reflections, and inserting 0 columns, but it will always look like this. But part of the talk is that actually the BCW is kind of the simplest way in which you can generate these cells, but also the simplest ways in which you can do things together. But somehow the physics of amplitudes was only associated to this way of building tiles, which are the BCW tiles. So it's in some sense literally the simplest possible, but meaning that if instead of these purples, when you insert something more complicated, you can still get something. But I will mention this only in relation to cluster algebra, not in terms of the Amplituhedron today. But I also have to move on otherwise. Okay, so I was mentioning that how do we find the aim is to find this collection of compatible cluster variables that describes our tile in a recursive way. But how do we find this? So for this, it's useful to look at the definition of cluster maps, which I also, a cluster map, so a map psi from two cluster algebras, A prime and A. I call it a cluster map if it maps any collection of compatible cluster variables in the cluster algebra A prime into a collection of compatible cluster variables in the image cluster algebra, up to Laurent monomials in the frozen variables. So I'm just giving this operational definition because that's actually what we want, it's used. So in practice, if you start with a collection of compatible cluster variables for the cluster algebra A prime, then applying these maps to a single one will give you a new cluster variables for the cluster algebra A times some monomials in the cluster algebra, times some monomial in the frozen of A. Laurent monomial in the frozen. Okay, so of course this is, I kind of simplified the framework of cluster quasimorphism. If you're an expert, this is basically the framework you have to look at. But basically this is the main property that for today we want to consider. And why is it useful? Well, because we show that there is a cluster map that interplays very well with the BCFW recursions. In particular, if you have a BCFW cell that is obtained by gluing a BCFW cell to the left and a BCFW cell to the right, then we show that there is a cluster map such that the collection of cluster variables that you need to describe the bigger cell can be obtained as the image of a cluster map of the collections of cluster variables for the smaller ones. And beyond the details, that shows basically the idea is that if you have collection of cluster variables describing your smaller BCFW tiles, because of the property of the cluster map, when you apply the cluster map to these two, you will get a compatible collection of cluster variables. And the nice thing is that also this collection of compatible cluster variables that you get by applying the cluster map is relevant for the BCFW to describe the bigger BCFW tile. So let's say recursively, the fact that we can generate compatible cluster variables for BCFW tiles relies really on finding a cluster map that you can apply recursively to generate new collections of compatible cluster variables. Okay, so now the question, of course, is how do we find these cluster maps? Like, how do we generate? Yes.
Like, how important is the core here? Like, are there other cores that you still get the same theorem?
I mean, this is the whole point of of our work. Yes.
Oh. Okay.
Yes. We conjecture how to generalize this for. Yeah. I mean, the spoiler is that every intersection number one cell would give something like this.
Okay.
So this
is core like
this is the simplest intersection one number cell ever in M equals 4. But for any M and for any K, we expect that any intersection number one cell used as a core will give you, I mean, you have to attach things in the right way, but would generate some kind of cluster map.
So this is like the BCFW is like the simplest.
Yes, exactly, the tip of the iceberg. Okay, so I'm not sure. Okay, so let me give you an idea on how to define this map. Sorry, I know I'm switching sides, I don't know why. Okay, so this was our Playbic graph for the BCFW tile. Let's start from the core. Let's consider the core, which is this thing, and let's make it bipartite, meaning that we add some black vertices that they're still in the same equivalence class of Playbic graphs, but they're just for convenience. So what we do is, for each black vertex, we associate a vector in C4. And the external ones I will denote it as Z, and the internal ones as B, just for convenience. Then what we do is that for each white vertex that we find, we want to impose a linear relation among the vectors associated to the black vertices that touches the white vertex through an edge. So for each white vertex, we want to associate a linear relation between the vectors sitting on the black vertices that are attached to the white vertex using an edge. For example, for this white vertex, I want to impose a linear relation between these three vectors. So I want V1 to be in the span of ZA and ZB. For this white vertex, I want, for example, V2, for example, V1 to be in the span of V2 and Zn, and so on. So there is, I want to have a collection of vectors and a set of relations for each white vertex. This is also what we call in our paper that is also related to previous works by in the literature called the vector relations configurations. But the novelty here is that the vectors that we put here are in C4, whereas the Plebig graph that we're using in general is in grk, n, or it's totally it's the vectors, let's say, that are putting here are in C4, but in principle you can put here any other Plebig graph and do the same things. But let's stick with this example. So now the thing is that in this specific example, we can solve the conditions. We can solve every internal vector in terms of the external ones. Meaning that if I impose all the linear relations I mentioned, there is a way to solve them, to solve V1 and V2 in terms of the external vector Z. Here there are some details, but for example, you can show that V1, for example, is in the span of ZA and ZB, but also is in the span of ZC, ZD, and Zn. So you can think about to be in the intersection of a true plane and on the free plane, but since we are in C4, that gives you only a one-dimensional subspace, and since these vectors are defined up to scaling, that up to scaling is fixed.
Maybe it's just good to say that 4 equals the m of the amplitude.
But this is for the m equals 4. Oh, this is only for the BCW. I will make the general case. Yes. Yeah, you're right. So the 4 here is because we are looking at the BCW for the Amplituhedron m equals 4. Okay, so in this way, basically, you can show that for this core, we can solve V1 and V2 in terms of the external ones up to scaling. And we call this, and we use these vectors to define a map. Okay, so what we do, then we insert a left blob and a right blob here. And we can think about the left blob as being somehow the Grassmannian 4, NL, where NL are the labels that you can read from the boundary disk. So A, B, N, and whatever labels you have here. And the GR4, N right is the Grassmannian on the right with labels that you can read from here, B, and all these labels here, C, D, N. So there are two Grassmannians. And this map, this construction generates somehow a map on the cluster algebras of the product of the two Grassmannians into the bigger Grassmannian GR4, N, which is the Grassmannian associated to the whole picture. And what we do is that if you are on the left Grassmannian, we substitute the column of the matrix representing a point in the left Grassmannian by simply seeing, okay, the label B is attached to the vector V1 using this edge. So we're going to substitute, instead of the column B in the Grassmannian left, we substitute it with the vector that is basically up to scaling equal to V1. And on the right, we look here, and everything else is left invariant because A is substituted with ZA, so nothing changes, and N is substituted with Zn, so nothing changes, and everything else is the same. So only the column B in the Grassmannian left is substituted with the vector V1. And similarly on the right, we do the same. So we look at the labels in the disk, and we see that to the column of the Grassmannian labeled by N, we have to substitute a vector that's proportional to V1. And to the column labeled by D, we have to substitute a vector that's proportional to V2. Okay? So this induces, you can see that is a map going from the Grassmannian 4, N to the product of two other Grassmannian, and the pullback of that map generates a map between the polynomial rings of the corresponding Grassmannians. And I want to see this as a cluster map in a way. So I'm going to mention the examples on how you can apply this map to some Plucker coordinates, for example, of the smaller Grassmannian to generate something new. But the construction happens in this way. Okay, so let me give the example. So if I start with the Plucker IJLB, I think there's a Plucker coordinate in my left Grassmannian, where IJL are smaller the IJL are bigger than B. I hope that I articulated it correctly. IJLB is a Plucker in the smaller Grassmannian. Then I have to substitute, by applying the map, I have to substitute the vector B by this vector here. And this vector here is a linear combination of the vectors ZB and ZA. And if I substitute, then the numerator becomes this difference of two monomials. And then there is this denominator ACD. And I can rewrite this using this notation, which maybe will also appear in Heimstock. It's just that by definition, the numerator is called like a chain polynomial. And we recognize that this chain polynomial, which is equals to this quadratic here, is actually a quadratic cluster variable for the Grassmannian 4, N. So this is to show an example that these maps that I define here takes basically these Plucker coordinates into a quadratic, these Plucker coordinates for the Grassmannian 4, N left, to a quadratic cluster variables for the bigger Grassmannian 4, N. Okay, so this is what you observe. But in general, it was the original results of our paper is that this psi BCFW is a cluster map, which means that it maps collections of cluster variables of the smaller Grassmannians into collection of compatible cluster variables of the bigger Grassmannian. And here up to frozen, because of course I always define this map by declaring some of the variables here to be frozen. For example, I declare the denominators to be frozen variables in the Grassmannian. So that's up to monomials in the frozen. I do get this. Okay, so and this really allowed us to compute recursively collections of compatible cluster variables for BCFW tiles from the smaller ones. So this is something that we used in the paper. But okay, maybe I move to the general constructions and then you can ask questions because this is maybe more important. So the key point is that instead of starting with this core, as maybe Stephen was asking, this is the core we use for the BCFW one. We can start with any Plavy graph that has intersection number 1, even for any m. So wherever there was a 4, before now there is an m. We can make it bipartite, for example, like adding stuff. And then we do the same thing. For each black vertex, we add a vector zi in Cm at the boundary. And then we add these j in the internal ones. I mean, the Plavy graph doesn't have to be a tree. Can be any Plavy graph that has the property that is intersection number 1. And for each white vertex W, so for example for this one, we impose a linear relation among, so it means a linear relation is sum over some coefficients RB and vectors VB, where the vector VB are the vectors sitting on the black vertices that touch the white vertex by an edge. And these RB are non-zero coefficients, okay? Then what we do is that then we want, in principle, to solve if we have all these relations, we want to solve every internal vector in terms of our fixed boundary vertices. And we show that this is the fact that this has a unique solution, so that if you fix external vector zi, the fact that this problem has a unique solution up to scaling is equivalent to demanding that the Plavy graph of the core has intersection number 1. So in general, the number of these what's called vector relation configurations up to scaling equals the intersection number of the core. So this is also part of the result. But for now, I'm just using it as it's an important result, but I'm using it as somehow something that which makes this set well defined. And finally, what we do is we place disks inside each face of our Plavy graph. So in this case, we place a disk here, I place a disk here. We can also place a disk maybe here or a disk here. I mean, there's freedom to place disks. And then for each disks, we denote DL to be the boundary. So D1 is this boundary here, and D2 is the boundary here. And then what we do is that we connect the boundary of these disks to black vertices of our core in a way that the edges, I mean, in a planar way. So we get a planar graph at the end. And then what we do is that, what happens is that we want to have such that, each boundary vertex on the disk is connected to a black vertex. So there is in a sense in which we can associate to each label of the boundary vertex on the disk a vector VBU, which is a vector sitting on the black vertex connected to the vertex U. So remember, before, every black vertex in the core has a vector, and the internal ones are fixed by the external ones by all these relations because it's intersection number 1. So this vector VBU will be a function of the external vectors, and we want somehow to feed it in inside the disk at this location U. Okay? For now, this is just a combinatorial definition, but what we want to do is define a map, which we call the promotion map. And the promotion map, it goes from the product of all the Grassmannian M, NL, where NL is the label sets that you can see on each disk. So here we have, for example, in the BCW, you have 2 Grassmannian left and Grassmannian right, but you can have as many blobs as you want, in principle. And then on each Grassmannian, we define a map on the polynomial ring, which means that whenever you have an expression in Pluckers that involves a label U on this Grassmannian, you want to substitute it to a vector, the vector VBU, which is the vector was attached to the label U in this way. So you, instead of the column vector VU in the Grassmannian, you want to associate the vector VBU, which is sitting here. It's basically what we said we did before for BCFW, but this is like kind of a procedure that we want to do in general. And also there are some studies like in principle you can, since this map is defined, these vectors are defined up to scaling, there is some freedom in the scaling. So let's say we choose some scaling. We also call this let's say the information of the core with this collection of disks connected to the core in this way. We call it a Playbit tangle because it was inspired by the planar tangles and works with the Jones and planar algebras. And there are other properties of Playbit tangles that are associated to composing them, and also we want maybe to impose other regularity conditions on them, but I'm not going to mention today. I'm just going to want to mention the general idea for them. Okay? So before, so this is the main proposal is that we want to use promotion maps generated in this way via Playbit tangles as cluster maps on the Grassmannian M, N, meaning that somehow there is a way in which you can take a Playbit tangle and define these maps, and these maps will be cluster maps, meaning there will be cluster quasimomorphism from the cluster algebra of the product of the Grassmannians to the bigger cluster algebra of the Grassmannian M, N. Okay? In particular, this says that, let's say for intersection, as a slogan or a summary, is that the intersection number one Playbit graphs somehow generate cluster maps on the Grassmannian. And if we specialize for m equals 4, that means that every rational Yangian invariant can be somehow thought as generating some kind of cluster maps. And in general, also there is a relation to Amplituhedron tiles, because as I mentioned before, let's say that for m equals 4, maybe for even m, still the relation has to be clarified, but let's say it's a good approximation to think also as intersection number one Playbit graph as the ones giving you tiles in the Amplituhedron. So somehow the way you define cluster maps is also corresponds to also some tiles. As before, if you fill this in, for example, with some Playbit graph of tiles, you can think as the whole thing as a Playbit graph of a new tile. So there is a relation with tiles, but we haven't explored this in this paper. It's for future work. Okay, so this is maybe let's say the idea. We're going to, in a paper, we're going to mention a bit more details like what is the exact conjecture, but this is maybe the main idea. Before moving on, I also don't know how much time I have, but it's very flexible, so this is the main idea. I have some examples and some other things I can say, but first I can stop here just to see whether you have questions. Yes?
You might tell me that this is more natural in the context of m equals 6 or higher, but even in the context of m equals 4, is it not interesting or useful to consider scenarios where you promote from a product of 3 or more Grassmannia? Like you have a tangle where you have to insert 3 blobs or more.
Yes. In principle, you can do that. So you can generate tiles. So you can generate Yangian invariants by gluing 3 other Yangian invariants. I still don't know whether that generates a tiling, a recursion for the tiling. So maybe I can show you then one thing. Sorry, I skipped this. Okay. Let's see. Okay. So I want to mention that for m equals 4, there is the next thing after the BCFW is a so-called Spurian. So this is a k equals 2 core. The BCFW with a k equals 1. And this is a rational Yangian invariant that has no physical pole, as 9 quadratics as poles, and there is no physical pole. But so you can use this to generate tiles. So you can put 3 blobs, for example, one here, one here, one here. You can also open it up in different ways and put 3 blobs. We don't know whether that generates an analog of recursions for tilings. What we know is that in our previous paper, we showed that actually this tile, gives a tile and appears in a tiling. So this object here is not a BCFW cell, but it still appears in a tiling of the Amplituhedron. So it's something that cannot be derived from any physics recursion, because this is like totally non-physical, or at least it's not in a standard way. There is no way in which you can start from deforming your amplitude in the BCFW way and get an amplitude which has this as a tile. So it's a good question to see whether this brings you new recursions for tilings. Okay. Yes, maybe I can mention this. Maybe it's clarifying. So what we did is so people who have maybe a bit less intuition. So what does it mean to have intersection number 1? I mentioned it's related to the degree of the Amplituhedron map thought in the complex settings, and maybe related to whether the map is injective on the positive settings. But maybe a nice thing is that we classified all the intersection number 1 cells that are associated to trees. So if your cell is a Plaby graph, which is a tree, then we give a very precise combinatorial criterion, necessary and sufficient, to tell whether it's intersection number 1. So you can stare at them. And we call these amplitudes because each one is a rational Yangian invariant, of which the simplest is the BCFW one, but the others are more complicated, and the spurion is one of them. I don't know if okay, so the combinatorial criterion is if you have a Plaby, if you start with a tree, and you cut each edge, you cut one edge in 2 parts. So you start with a tree, you cut one edge E, and then you assign half edge to one piece and half edge to the other component of the graph, so you have 2 graphs. Then there is a criterion to tell whether, a criteria that you have to satisfy, so the smaller graphs, GI, are of type Ki, Ni, and there should be a relation between the Ki and Ni that is related to M. So this is like some inequalities that your smaller pieces, G1 and G2, have to satisfy. This is just a combinatorial criterion, but we basically, in this way, classifies all the intersection number 1. Just as an example, for k plus 1, this is the only one, and this is the BCW. For k plus 2, up to, this is one of them, and this is the spurion, what we call spurion. For k plus 3, this is also an example, which we call a chain tree. I mean, chain tree maybe is a kind of class of example. And anyway, like for every k, this is goes up to any k. But I also want to mention that there's some numerology, so there's some way of counting how many there are, like we have in our paper. But anyway, just to say that the BCFW that we've seen so far is only like the tip of the iceberg for that. And basically for these ones, these ones we already show in our previous paper that generates a cluster map. In the upcoming paper, we also show that this spurion generates a cluster map, and also this chain trees generates a cluster map, meaning that if you stick some blob in a certain way, then it gives a cluster map on the smaller Grassmannian and so on. So this is basically the main idea. Okay, so I think now it's flexible. So there are 2 options. I can maybe show this. Okay, I think I have to ask the. What do you want me to do?
Maybe you can finish up in a couple minutes, and then we can take more questions.
Yes. Okay. So I will skip. So here I have the example of the spurion. So maybe you can ask me later. What I wanted to say is that I wanted to move on and ask the following thing. So what happens beyond intersection number 1 cells? So if we place as a core an intersection number 1 cell, I can generate these cluster maps. But what happens if I place an intersection number 2 or higher? I could play the same game, meaning I could place some boundary vertices, some boundary vectors, Zi up to Zn, and then I can try to solve the internal vectors using these linear relations imposed by the white vertices. But as I mentioned before, if the intersection number is higher than 1, then we don't have one solution. We have D solution. If the intersection number is D, we have D solutions. And this is not the only new feature. The new feature is also that we cannot express the internal vectors in terms of the external vectors only using rational functions. We have algebraic functions. So in this example, if you consider the purple as the core, which is what physicists call the four-mass box, because the Yangian invariance corresponding to this Plaby graph is the one associated to the leading singularities of the four-mass box. Then if you try to solve V1, okay, I put V1 here, X and Y and V2. So these are 4 vectors. And you can solve, there are 2 possible solutions. You find, for example, that X is expressed as a linear combination of 7 and 8. These 2. But the coefficients, they're called alpha plus or minus, is a bit complicated. It's an algebraic function. I put plus or minus because there are 2 solutions, as I mentioned, since this is intersection number 2. And alpha is expressed in this way. This is like, you can recognize the formula from high school and middle school. But then for solving a quadratic equation. And delta is a discriminant that also appears as a discriminant of a four-mass box that is related also to the real Schubert problem, to the existence of intersection of a certain problem associated to the four-mass box. And usually I think in physics it's not written in this way. We wrote it in a way that exposes the connection to cluster variables. So B is the sum of 2 cluster variables that are quadratic, and A and C are exactly 2 cluster variables which are quadratic. Okay. So there is this magic property somehow that delta is positive on the positive Grassmannian, which is not obvious. Okay, so what do we do now? The point is that we can still think to use these objects to define a map on the smaller Grassmannian, meaning we want to think about the Grassmannian 4, n prime, where the n prime is labeled 1, 2, 7, 8, 9 up to n. And instead of a vector, instead of a column labeled by 7, I want to substitute this vector x that I have attached here that flows inside. And this vector, as I mentioned, is a linear combination of two vectors with their algebraic coefficient. So what happens if I cannot define a cluster map in a traditional sense because the promotion of a cluster variable is an algebraic function. Okay, no, here is just the proof of that. Okay, so what happens, I just expressly, so if I apply psi, this map to Plucker coordinates, 1, 2, 7, I, so 7 gets mapped into 7 plus alpha times z8. So you have 7i and t8. So this is the sum of two Pluckers with the alpha, right? So this is an algebraic function, the Grassmannian. So I cannot claim that's a cluster variable for sure. So what can I say? What we show is that actually the property of cluster variable is not, it doesn't make sense, but the positivity property is preserved. So we show that the 4 max box promotions preserve positivity of cluster variables of the Grassmannian, meaning that if x is a cluster variable, the image of x is positive on the positive Grassmannian, gr4, n. Okay? So in particular here, the fact that this is positive is non-trivial because each Plucker is positive on the positive Grassmannian, of course, because that's how the positive Grassmannian is defined. But you can check that alpha plus or minus is negative on the positive Grassmannian. You can see it here because delta is slightly smaller than b. And then you have minus b plus square root of delta. So for sure that's negative. And A is a cluster variable, so it's positive on the positive Grassmannian. So you can see that alpha plus or minus is negative always on the positive Grassmannian. So the fact that this combination is positive on the positive Grassmannian is very non-trivial. You have to, as for cluster variables, it's non-trivial that they are positive, right? If you don't know that they come from a cluster structure. So in particular, so this is basically one result that independently of what cluster independently what cluster variables you pick, you apply this map and you get something that's positive. And okay, mathematically it's very interesting, but also physically is interesting because the images of this psi map are actually singularities of Yangian invariants that they appear when for n greater than 9 and k greater than 3. So if you want to write your amplitude for n greater than 9 and k equals to 3 at loop level, for example, you might need the Yangian invariant that has singularities that are images of these psi maps. And this tells you automatically that it's positive on the positive Grassmannian. My last slide. Why would you care? Well, because of this statement. There is some kind of feeling of the community, and Mark told me, he also expressed it in 2024. Well, basically, there is a belief that the scattering amplitudes in n equals 4 superior mills are regular on the positive Grassmannian. That means if you there are transcendental functions and there are some algebraic singularities, but they are still regular on the positive Grassmannian. What does it mean? That every singularity of the amplitudes is maybe the vanishing of some function, and this function is strictly positive on the positive Grassmannian. Okay. So as to conclude, to bring everything together, when this singularity is rational, then it is conjectured that it is a cluster variable, and then of course every cluster variable is positive on the positive Grassmannian. So by the major property of cluster algebra, which is Laurent positivity, that shows cluster variable are positive. So this, if you understand that that f is a cluster variable, then positivity follows. And also from our work, somehow it suggests that the singularities of all rational Yangian invariants are images of cluster promotion maps that are induced by some intersection number 1 cell. So, and the fact that if this is true, then it follows automatically that there are also cluster variables. And so it follows positivity. But in general, when f is algebraic, for example, these algebraic letters, singularities of non-rational Yangian invariants, there is no general mechanism that will explain positivity. Meaning, why would they be positive on the positive Grassmannian? There's been some work about limiting rays and cluster algebraic functions that it might give some framework or some explanation, but we saw basically by before that the singularity of non-rational Yangian invariants we expect to be also images of this promotion map where the core somehow has intersection number greater than 1, but somehow the positivity should be preserved. For now, let's say it's a conjecture based on only the 4 mass box example, but we're going to work also on finding intersection number 3 and others. So so this is basically the relation to positivity, and in some sense there is some notion of positivity that emerges, a mechanism that gives positivity from these promotion maps. Okay, I think I'm basically done. I just want to mention the last two things. One is that cluster promotion maps, in principle, from the commutative algebra point of view, they can shed light also on the cluster structure, because they tell you many ways of generating cluster variables. So understanding like which ones are cluster variables, how they're compatible. There are many open problems in the theory of cluster algebras in the Grassmannian, but they're of course also relevant for physics. And for the Amplituhedron, as I maybe mentioned a bit, is that as for the BCFW, we could use and we will use cluster promotion maps to describe tiles and detail images of positron cells beyond the BCFW case. So this is how we think about them. And finally, of course, we are also asking like, okay, the Yangian invariants are more or less like singularities of Yangian invariants, both rational and algebraic, could be understood conjecturally using these maps. But what about the letters that appear in the symbol alphabet? Are they also images of promotion maps? And this would be very helpful, both because it would prove that they're cluster variable, because they're positive, because the compatibility is preserved, and many other properties that might be nice to explore. Okay. Thank you very much, and for the time and the attention. Yes.
Thank you. Do you have more questions?
Okay. Well, you choose the order.
No, you can.
Oh, okay, Omer. Okay, that was the first one.
One question or comment. Question is, you said the NAT-psi preserves compatibility. Does it also preserve the exchange relations?
Yes.
Okay, I thought I expected.
Yeah,
that.
so,
Because we see exchange relations between algebraic letters in some quantities, so that might explain that, which is great.
Yeah.
And the comment was: is this the smallest, the simplest delta you see? Because in the discriminant that you see, the scattering amplitude at 8 points at least, the -4, b squared minus 4 minus ac, I think that you have there, is 4f, which is made out of frozens only. But your things look.
So, okay. Yes, it's the same. I realized that this was different than the one in the physics filter show, but then I checked they're the same.
They're the same. Good.
Yeah. So just this was written explicit in terms of. Well, also I guess yours is written in terms of cluster variable because there are Plukers, but I guess it's like weird combination of sums of monomials into Plukers. This is just a very simple like sum of quadratics and difference of quadratics. So it's, I don't know. I mean, the positivity is much easier to see here, I think. I mean, the positivity of the alpha. What I mean, the delta is still, I don't know the positivity. I mean, it's not clear, of course, the positivity there. Yes.
Is there a notion for promotion for the flags?
Yes, that's a good question. Yes, I mean, it's related to other works, but yes, we also define promotions. I mean, we can define also promotion for the flags. I mean, in that case, there is not much relations to Plebby graphs. At least, okay.
Of course not.
If you embed the flag into Grassmannian, maybe yes. But yeah, we do have also promotion for flags. They would
paper, or you have it in some notes, or you have.
Okay, so currently, I mean, we have one, but it's relevant not for what you think; it's for something else.
It's in some unpublished notes. Or in some...
I mean, we have at least 3-4 papers that I've been writing, so I don't know when they will be published. That's it's a math timescale, so. But yes, so I mean that is relevant, I guess, as you might expect for the momentum amplituhedron, but also actually to understand even the inside the Grassmannian, for just promotion map in the Grassmannian. Sorry, there were questions there. Yeah. Yes.
So something like the 4-mass box promotion, you said, oh, well, this can't be a cluster algebra morphism in the classic sense because it's sending things to cluster variables, things that aren't cluster variables. Is there any way that you could generalize cluster algebra morphism to send like cluster variables to theta basis elements in a way that you could then say, oh well, we're sending cluster variables to distinguish basis elements even if they're not actual cluster variables anymore.
What kind of basis you said?
I said theta basis, but just as like some preferred
theta basis you said.
Some preferred basis that extends cluster variables so that you could talk about something like that.
Yeah, it's a good question. I feel like what we've been thinking is like kind of a Galois extension of a kind of cluster algebra, meaning that you are introducing also the square root of delta. And that means that, for example, a cluster variable that before was not factorizable, then it kind of factors, it's reducible because you can write it as a product of two, where each one has a square root. But then I think it's very tightly connected to the question of what cluster structure do you associate to the 4-mass box itself. And because, I mean, now in some sense, so if I go back 1 second, so what you can do, I mean, the way we prove this is that we took an initial seed for the smaller Grassmannian, I applied this promotion map, and I checked that all the functions obtained are positive, and then since, I mean, every cluster variable of a smaller Grassmannian can be written as a Laurent Laurent monomial with positive coefficients in terms of the initial ones by promotion and everything. I mean, you can use this method to physically prove, but then you can also think about the promoted seed as some kind of subset of the cluster algebra, of some kind of generalization of cluster algebra, because it contains also algebraic functions that are images of the whole initial seed of your smaller Grassmannian. But the question is, how do you complete it to make the bigger one? And we suspect, of course, you have to think about first, what is the cluster algebra associated to the 4-mass box? But for example, I mean, looking at the facets of the 4-mass box or the discriminant, and I guess you can try to imagine what is the maximal collection of independent functions in the kind of Galois extension of the ring. So I think that could be done. And then everything, I mean, exchange relations and things should be also followed. I mean, it would be fascinating. That's what I think should be done. Yeah.
Do you know or expect that every cluster variable of GR4n is a facet of some tile?
No.
You know it's not true? Or
Yeah, because if you fix n, there is a finite amount of them.
Yes,
We
of course.
cannot get all
Obviously.
cluster variables
Yes,
from
okay.
Yeah.
So do you know how to okay, obvious, okay.
Yeah, no,
I'm done.
I mean,
Yeah,
I understand. I think your question is has the same flavor of our question you asked me about, and it's. I mean, I agree. It's a very interesting question. I don't think we understand
Okay.
what kind of finite collections we get. Why is it special for the cluster algebra and the Grassmannian itself? But I think it's related to the question whether you can use just the poles or singularity of Yangian invariants as letters for your simple alphabet. I think it's a physics version maybe of what you're asking for. Yeah.
All right, let's save further questions for the break, and thank Matteo again.